So moving on, let's talk about phase transitions. Okay, so we can come up with this equation. So we note that the thermodynamic definition of entropy, right, is this dq reversible divided by temperature. Okay, but we also know that Q at constant pressure equals delta H. Okay, so another definition, another mathematical equation for entropy, delta S, so I'll just write this generally, delta S is delta H divided by T at constant pressure. Okay, and now this TRS, okay, that stands for phase transition. And so now specifically the entropy of a phase transition is the enthalpy of the phase transition divided by the temperature at which that phase transition happens. Okay, and so here is a graphical representation. Here's for water. And so what you can see here, entropy, so we, as a function of temperature, right? So we're going to have to come up with some way of calculating this line, and we will in the next slide. So this is, you know, I'm just saying molar entropy of the solid as a function of temperature, molar entropy of the liquid, or molar entropy of the gas, okay? And so, but now you notice that it's a discontinuous function, right? So at the phase transition, there's this huge jump. Well, that is this value right here, okay? So for example, that delta S standard of fusion, it equals the delta H standard of fusion divided by the temperature at which that happens, okay? And in the case of water, you can see that that's 22 joules per mole per K. For going from a solid to liquid, you can see going from a liquid to a gas, it's much, much bigger, which is not that surprising because there are far more microstates to describe a gas than there are that describe a liquid or a solid. So it's to be expected that there is a much bigger entropy change associated with going from a liquid to a gas versus going from a solid to a liquid. Okay. What's also pretty cool is we can use this relationship to start to conceptually know when a phase transition will be exothermic or when will be endothermic. So I'll show you as an example. Come up with 2 examples of exothermic phase transitions and 2 examples of endothermic phase transitions based on this consideration of delta S. Okay, so let's write that again. I'm going to drop saying the TRS, and we just know delta S equals delta H divided by T. Okay, so for example, and you can pause it and think about this if you like. I'm just going to keep moving forward. Okay, so suppose we go from a solid to a liquid. Will that be exothermic or endothermic? Okay, well, what do we expect for delta S out of this process? Okay, well, we expect delta S going from a solid to a liquid should be greater than 0, right? A liquid is, if you will, more chaotic than a solid, so we know there is an increase in entropy in going from a solid to a liquid. And because in this case delta S is greater than 0, then that means, therefore, delta H for this process has to be greater than 0. And that makes good sense, right? To melt a solid into a liquid, you have to put heat in. That makes good sense, okay? And so, for example, if we think about now going from suppose a gas to a liquid, what happens to delta S? Okay, well, a gas has a lot of microstates. It's fairly chaotic, okay? A liquid has less. So there is a decrease in entropy in going from a gas to a liquid, all right? Correspondingly, there has to be a release of heat. So this is an exothermic phase transition going from a gas to a liquid. And we might not have been able to guess that right away, but when we use this relationship, delta S equals delta H divided by T, then you get the right answer every time, because I think it's fairly straightforward for us to remember our entropy from the Gen Chem days, right? When we go from a solid to a liquid, that's an increase in entropy. Another one, liquid going to a gas, that would be a positive delta S and thus a positive delta H, right? But then now going the other way, going from a gas to a liquid, that's a decrease in entropy. Correspondingly, that decrease in entropy will release heat into the surroundings. Okay. So I'm going to move on from this because I think I could talk about this over and over and over and over again, and that might be best for a discussion. Okay. So moving